All right, everyone, it is my pleasure today to bring you the hands-on session on yield modeling. And I must give full credit to Dmitry Savransky because he programmed this whole tutorial as well as the group project that you'll have the opportunity to work on tomorrow. But I'm the one in the room, so I'm the one that is going to lead you through this, and Dmitry's online in case we need additional help or commentary. Now, if you're in the room, we have hands-on helpers. So if you are a person that is in the room that can help with this particular notebook, raise your hand now to say that you're a resource. All right, we've got Corey. We've got another person in the back. We've got three over here, sort of. All right. Know where these people are in case you need some help. Now, the first thing that we're going to do is get set up on the notebooks. Oops. Okay. And so the first thing that we want to do is the setup. Wait, is that this tab? Right. So if you have not yet run the yield modeling tutorial setup, this is the first thing that you're going to do. And please note that there are blue dots and there are orange dots. And you want to do all the things that have orange dots if you want to run this in Colab. If you would prefer to run this in Python on your notebook in not an online fashion, then you want to do the things with the blue dots. So I'm going to walk through this like I'm doing the setup. Here with the first orange dot is to, and here, this is not the tutorial yet, we're just getting set up. And so you run these cells. It's going to mount, the first thing is that it's going to connect to the Google Drive. And I need Melanie to come up and do her two-factor authentication because we're using her Google Drive. Thank you, Melanie. All right, so we have mounted our drive here. I'm going to run the next cell, which is all, and all this is going to do is it's going to define the working directory for us, and then the next cell. We're creating the directory. You don't have to do any inputs, just run these cells. And then we get to the blue section. So if you're downloading this to run locally on your computer, do the blue cell. I'm not going to do that. I'm using Colab here for the demo. And now we can go to the notebook with the tutorial. And we still have a little bit more setup to do. So here, since I'm using Colab, I'm going to follow the orange dots, and I think we've already mounted the drive. So maybe I'm doing it again. All right. All right, happily Google thinks Melanie is still logged in. And again, I'm going to connect to our working directory. And now this cell is the one that's going to install a bunch of stuff, and this may take a minute or two. I'm scrolling down so you can see how much stuff it's installing. All right, the very last line is it says successfully installed SSW yield modeling tutorial. And if you get to there, then you have installed everything. And we need to install the Jupyter widget. Getting that done. And then, let's see, still moving through tutorial setup. This is actually the start of the tutorial. We have to import all these packages that we're going to use, and then we also have to import plotting. And now I'm ready. Are you guys ready? We're going to begin the tutorial. We're going to take a journey in the tutorial from what are our observables to how we can actually find out if it's feasible and how we schedule a mission. So there's a whole arc. We have 9 exercises in here. There's you'll note that there's a lot of text and there are some equations in the text. I'm not going to stand here and read you all the text. That's not the point of this. This tutorial is actually pretty standalone. In fact, I could probably like sit down right now and you guys could work through it on your own. But that's not as exciting as having me up here telling you about it. So I'm going to go over some of the basic concepts with you. And then there will be exercises in which you will get to write code, in which you will get to make plots. But most of all, we hope that you will understand some of the building block concepts and doing yield code. So what are some of those building block concepts? They are, what are our observables and how do you calculate them? We are going to also look at completeness. So we're going to learn how to calculate completeness. Chris talked a lot about that this morning. It's pretty important. We're also going to learn how to calculate exposure times, because that's very important. And we are also going to look at, is it feasible? Can I actually make this observation? And then we're going to look at how long would it take to observe over a whole target list. So that's the journey that we're going on today. And we are going to start with what's observable. So our measurable quantities. So here we're looking at a diagram to get our coordinates set up. Any of you that have worked on an engineering project with multiple disciplines will understand the importance of establishing your coordinate system. I have an optics background. Z is the axis that goes forward and it goes from right to left. I'm sorry, from left to right. It goes that way. But if you talk to a mechanical engineer, Z points up in gravity. So if you're engineering something in space, the most important thing is to get your coordinates set right away. So just to let you know, this is the coordinate system that we're using, and this is the coordinate system that Exosims uses. Now we're using pieces, we're having you write sections of code that are nearly identical to some of the code that we have in Exosims. We're not actually exercising Exosims today. What we're doing is we're having you build the building blocks that go into Exosims and into another code if you wanted to write it that is similar to Exosims. All right, so first and foremost, let me figure out the pointer here. Oh yeah, no, I've seen this. I've seen a few presentations. I know that I have to come up here. There we go. So we have the sun, it's yellow, and we have the planet, it's blue. And this is no pink on this screen. This is the plane of the sky. And so what we can observe is the brightness of the planet and the projected separation onto this plane of the sky. So now I'm scrolling down to this first equation, which is, so if we, before we figure out the projection, we want to know what that vector is and how we calculate it. So the first thing that we're going to do is we're going to set up the how we rotate the planet's orbit. And the clues are here for you guys to work through. So here, I'm going to play this cell. And really what this does is it sets up the equations for rotation. Similarly with the next cell. And now we can use these equations to find the projected separation in a somewhat simplified form. I mean, this is a lot more simpler than looking at the matrices of equations we were just looking at. All right, so now we have an equation for the projected separation. And that equation is only a function of the orbital radius vector magnitude and the inclination and the argument of latitude. What we'd like to work on next is the delta magnitude parameter. And so to do that, there are a couple of important things that we have to know. We're going to using beta as the separation angle. And then we have to choose a phase function, and we are going to assume, for the sake of modeling, a Lambert phase function, which is the phi that you see here. So it varies with the planet's angle as it goes around the orbits. All right, so I'm going to play this cell next. Because we're just defining parameters, and now that is really the setup. And we're getting ready to enter exercise 1. I'm having a hard time reading the laptop from here with these glasses. So I'm going to have to dance around a lot. So what we're ready to do is write our first bit of code to be able to calculate these variables. And I'm going to give you a few minutes to do this, but I'm also going to preview what the resulting answer might look like. So I'm going to give you just a few minutes to get started here.
Rhonda, could you please show how they can access the reference solutions?
Yes, if you feel like you're stuck or you just like to see what the results are, we can come over here to the Google Drive. This is what you wanted me to show, right, Dmitry?
Yes, please.
All right, to the drive, to my drive, to
No, to SSW.
no, yep, this one. Oops, no, hang on. All right, so we're looking for the yield modeling tutorial down here that has the shorter name. We're going to drill into that. And then this piece of Python code. I'm going to open that up and it's going to bring it up over here. And there we go. And so then if you're stuck, you can see the reference answers over here in this section.
Okay, now hide the answer so people don't cheat.
So I've cheated because I've already done this. And I'm working out what the S and the DMAG would look like. What was the question? We have a question, which is the latitude in the diagram? You were asking about theta and the latitude?
Sorry, was that a question for me or?
Yes.
If the argument of latitude, if you look at the text, is defined as it's the sum of the argument of periapsis and the true anomaly. So theta is equal to little omega plus nu. And Rhonda, if you scroll down a little bit, there should be an equation that says that. right after the derivation of S. Yep, right, or sorry, right there. It's right before cell number 9.
Oh, well, I'm hard time hearing you. Here,
It's
this
right
one,
there. It's right beneath your cursor.
over in here.
A little bit down. Little more down. Next, down, 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 down. Stop. There.
Right over here. All right, thank you. Yes, we have another question in the back of the room. Have you gotten any of the cells in the tutorial to play correctly? Is this the cell that's not working for you? Okay, so in this cell, I've cheated, but what you guys are supposed to do is actually write in the equations for R, theta, S, and beta. This is your opportunity to write a little bit of code here. This is the exercise. All right, has anybody had a successful result on this cell yet? Yes? We have at least one person? All right, I'm giving us another 90 seconds and then we're going to move forward. If you haven't gotten there yet, there are two things that you can do to cheat. One is you can open this Python code on the right that I showed and copy and paste it over. Or the thing that I did to cheat, as I commented out these lines where I have to calculate these individually, and I instead uncommented this line where I'm actually using the tutorial function. And then just to convince myself it was working right, I added this print statement so that I can see what's happening here. Next, we're going to plot these. So you do need to have something in your workspace. You do need to have some of these values in your workspace. So if you haven't come up with your solution now by yourself yet and you want to move forward, now would be the time to cheat. Vanessa. All right. Sure. So Vanessa is making a suggestion that so far this week, we've heard a whole bunch of really fabulous things about coronagraphy and exoplanets and spectroscopy, but we've not yet heard about orbital dynamics. And that maybe we should spend a little bit more time there. And in fact, what I would like to do is ask Dmitry to do that because Dmitry is amazingly good at orbital dynamics and he's fantastic at teaching it. And usually when I have a question, I ask Dmitry about orbital dynamics. So Dmitry, I'm going to scroll back up to this diagram and I'm going to close this Python code. And I'm going to ask you to give the introductory explanation about orbital dynamics here.
Okay.
And speak loud and really close to your mic.
Okay. If I get too faint, please remind me. That was a really big buildup. So if I am terrible at explaining things, you have only Rhonda to blame for overselling. But very briefly, if so planets and stars, they orbit each other in very complicated ways, but for the sake of what we're doing here, we can actually simplify our treatment of orbits quite a lot. And we can go all the way back to the 17th century when there was this guy named Johannes Kepler who looked at observations of Mars and figured out that it looked like Mars was going around the sun in what appeared to be an ellipse. And this became what is known as Kepler's first law. Planets orbit stars on ellipses, or more generally on conic sections, which is the intersection of a plane with a cone. So we don't care about any of that. All we care about is the planet is going around the star in an ellipse. An ellipse is a squashed circle. So the way that we describe the ellipse is by two quantities. They are the semi-major axis, which usually is represented by symbol A, and by the eccentricity. So the semi-major axis is half the major dimension of the ellipse. If the ellipse happens to be the special case of a circle, the semi-major axis is the same thing as the circle's radius. The eccentricity, denoted by symbol little e, is just the squashedness of that ellipse from a circle. So an eccentricity of 0 means that the ellipse is actually a circle. An eccentricity of 1 means that the ellipse actually is no longer an ellipse and becomes open. So those are the two things that we use to describe the shape of the orbit. And what Rhonda is highlighting right now is what's a thing called the eccentricity vector, which is the direction from the star to the point on the orbit where the planet is the closest to the star. All right, so we have two quantities now, A and E, semi-major axis and eccentricity. And then we need three additional quantities because this orbit is rotated in an arbitrary fashion in three-dimensional space. And the way that you encode arbitrary three-dimensional rotations is by using three different angles. It turns out that you can show that you need exactly three angles in order to orient a three-dimensional object like this orbit in three-dimensional space. The names of the three angles are the longitude of the ascending node, that's the capital omega. And then the second angle is called the inclination, that's letter I. And then the third angle is called the argument of periapsis. So that's so capital omega, capital I, and lowercase omega are the three angles that you need in order to fully orient your orbit in three-dimensional space. So we're now up to 5 parameters. Finally, we need something that tracks the planet's motion along its orbit. And for that, we can use a variety of different angles, but the one that we care about the most is this thing called the true anomaly that we symbolize by Greek letter nu. To simplify our expressions, we are going to also define another quantity, which is the summation of nu and lowercase omega, and that is the angle all the way from the plane of the sky to the current orbital radius vector. And we call that quantity theta. Finally, there's another angle that we can calculate, which is this angle beta. Beta is the phase angle, and it's very important. The phase angle is the illuminant object observer angle. So star, planet, you, or your telescope, or your space observatory. And if we make the approximation that the vector from the observer to the planet is exactly parallel to the vector from the observer to the star, which is an okay approximation, because the stars are so far away that those vectors are essentially parallel to one another, then we can simplify the definition of beta. And if you scroll down in the equations, they will tell you that the cosine of beta is related to the cosine of the inclination and the sine of the argument of latitude. So ultimately, what we need to calculate are these two quantities. We need to calculate the difference in brightness between the star and the planet. That's the delta mag. And we need to calculate the magnitude of the projected separation. So that's the thing that we call S. So this first bit of Python code just symbolically manipulates these equations and gives us an expression for S. So this is kind of a neat thing that you can get Python to do for you. If you need somebody to do your algebra homework, Python's on the case. So if you scroll a little bit more, that right there after cell 10 is the expression for S, and it is a function of just the magnitude of the orbital radius vector, and that magnitude is given in the very first equation in this section, and then trigonometric functions of the inclination and the argument of latitude. And if you keep going further a little bit, the delta magnitude, as I'm sure Chris told you, is the flux ratio between the planet and the star given on the logarithmic magnitude scale. And that flux ratio is parameterized by the geometric albedo, which we call P, which is a measure of the bulk reflectivity of the planet, the phase function, which is a measure of how the planet reflects light as a function of that phase angle, and finally, it is a function of the relative intercepted area of light from the star. And if you work out the area ratio, it's just the same as the ratio of the radius of the planet to the magnitude of the orbital radius vector, quantity squared. So you put all of this stuff together, and that allows you to enter the equations into exercise 1, which allow you to solve for all these values and then generate a pretty plot. And Rhonda, I think you should run the plot now.
Thank you very much, Dmitry. All right, so in exercise 1, then, we're calculating those key parameters and getting to the point here where we can generate a plot, which looks like this. And so if we're looking at as a function of the true anomaly, then we can see what are our two observables here, the separation and the delta magnitude. And what we'd like to do is, so we know something else influences this. We know that the inclination influences this. So now we want to add inclination into this. And we're going to, I'm sorry, I'm skipping ahead. We're not doing inclination yet. We want to see how this might interact with an instrument. So we're going to define what our inner and outer working angle bounds are. And we are going to find a distance and then what our limiting delta magnitude is. So the limit of how of that contrast that we think that we can see. So we play this cell just to establish those. And then as an exercise, if you would like to figure out, you have an opportunity to write some code here on what are the indices in that vector that I actually have access to given these new constraints. Preview of this for you. Right, sorry, this one. And now once we have the right indices, then I'm going to scroll back up to the plot and see what we've indicated for the constraints that we've just applied, where we have access to the delta magnitude and the separation. But so as I started to mention, I jumped the gun, that the orbital inclination also has an impact here. So we'd like to check and we would like to add that to our calculation. So I run that cell and I have a new plot. It's the same plot that we were just looking at, except now we have a slider bar up here. And we can check and see, we can go down to 0 inclination. So close to 0. There we go, 0 inclination. And now we have access to the planet everywhere because a 0 inclination is face on. So assuming that this is outside of our inner working angle and inside of our outer working angle, which we've cleverly engineered to be so in this example, then we can see the planet all the time and at all the magnitudes. We can go to the other extreme to be edge on. I don't think this updated.
No, edge on is in the middle. It goes from 0 to 180. So edge on is right in the middle.
Thank you. How come the eye slider only goes to 100?
Because I ran out of time and didn't make the slider actually represent the right number.
Okay. I'm sorry, that wasn't really a why. That was is this what I'm observing? All right. So all right. So I'm trying to find 990. Trying to find, there's a lag here. That doesn't look like edge on to me.
No, that's right.
I thought it was supposed to go to no.
I'm sorry, I didn't get that.
So I was trying to do edge on and I thought that it was going to 0 when we do edge on. Because we do face on and we have 100% access. Let's see. Pause here for a moment at 60. I can't get it right to 60, but I'm close to 60 degrees. A lot of times in yield modeling, we will use 60 degrees as a stand-in for inclination, because when you think, when you want to make something that is randomly uniform in angle, but you take a cosine of it, then the maximum probability is at 60 degrees. So you can cover a lot of bases by using an inclination of 60 degrees if you just need a quick assumption. Oh, okay. So I was about to say that I was going to move on, but that is in fact the end of calculating the things that we need in order to be able to calculate our observables. And the next section is completeness. And I see some folks that it look like I see some folks that are concentrating, that looks like potentially they're trying to write some code. And I see some other folks that look like they're ready to move on. All right, so what I'm going to do is I'm going to give everyone 3 minutes to continue the exercise here in writing the code. And then I'm going to move on to the next exercise. All right, I'm hoping by the level of conversation I'm hearing in the room that most of you have been able to complete this. All right, I see some nods of the head. That's fantastic. We're going to move forward to the next exercise in which we get to really focus on the joint probability of our two observables, also, which is going to lead us into completeness. All right. Okay, so where we're headed in this section is that we are going to make a bird plot like Chris showed you this morning from the Bob Brown 2004 paper. So we're going into the history of yield modeling, and we're going to make the bird plot. So we've already gotten the two most important pieces of this, which is how to calculate both our delta magnitude and our separation. And what we need, so we can do that for one planet as it changes places in its orbit. What we need now is a whole population of planets. So Bob Brown used Earth twins in the habitable zone. So all the planets were exactly the same radius as the Earth, and I think he used a single geometric albedo to describe the reflectivity, and he had them uniformly distributed from the inner to the outer edge of the habitable zone. And so Chris introduced this idea some that you can think about this shell of planets, and you can create like 10 to the 5 of them in this shell. And so now you've got them all, this cloud of planets orbiting in the habitable zone. And then we're going to project those, and then every single one of those dots can get translated into the separation and the delta magnitude for that whole population. And that is, in essence, what goes into making the bird plot And then we can treat that whole cloud of planets as a joint probability distribution function of completeness. But I'm getting ahead of myself. So we're going to use an assumption. Oops. There we go. All right. So we're going to use from 0.7 to 1.5 astronomical units. There's a lot of discussion about what is a habitable zone. And just for today, we're going to use this simplifying assumptions. And we're going to assume eccentricities that are uniformly distributed between 0 and 0.35. That's the reason we go to 0.35 is a historic number out of RV data back when RV mostly only detected large planets. And we're going to use geometric albedo of 0.367. And then we have to decide statistically also how we feel about the other parameters. So we're going to do the orbit orientation. We're going to isotropically distribute it over the unit sphere, i.e., we're not going to assume that there's a preferred orbital plane like a disk that all of this cloud of planets wants to be in, because we're trying to do statistics right now about this cloud of planets. And so little omega and big omega, we're going to consider to be uniformly distributed between 0 and 2 pi radians. And the inclination is sinusoidally distributed, i.e. this form. And we're also randomizing the time that we observe this population. So another way of saying that is that we treat the time of the observation as uniformly distributed. An implication of that is that the mean anomaly is going to have a uniform distribution. So we're going to use capital M for that mean anomaly. And that mean anomaly is the angle between the center of the orbit and the place where the planet would be at a given time if it was on a circular orbit of radius of the semi-major axis, i.e. if it didn't have eccentricity. And so the mean anomaly is related to the eccentric anomaly, which is capital E, by this equation right here. And then the eccentric anomaly maps to the true anomaly by this equation. There's one other more simplifying assumption that you can make, which is to have 0 eccentricities. But in order to do the Bob Brown plot, we are including these eccentricities. All right, so now we get to the exercise part of this. And in this exercise, what you're going to start out with in this cell is to program your values for what you think the semi-major axes, so A, what your values of A are going to be. And in essence, you want to do a random draw on a uniform distribution. So if you want some help, here's a reference right here on NumPy and their random uniform distribution. You also need to generate an array of eccentricity values that's uniformly distributed between 0 and 0.35, as we already discussed. And then we want to have a uniformly distributed angle between 0 and 2 pi on little omega. And then we want to have a sinusoidal distribution of inclinations. And there's a hint in the cell here to help you out with that. And then we want to generate an array of mean anomaly values, which is uniformly distributed between 0 and 2 pi. So again, if you get stuck, there's how you get to the cheat over here on the left. But also, I'm going to go ahead. I'm going to run the solution while you guys work on this, just as an example.
And so just for clarity, if you don't mind, I'll editorialize for a second. you'll notice that when I was originally describing the orbits, I didn't say anything about mean anomalies. And that's because ultimately we don't care about the mean anomaly, we care about the true anomaly. The only reason why we bother first computing the mean anomaly is that the density function, the distribution of true anomaly, is complicated and is hard to sample from. So instead of doing the hard statistical task of sampling from an arbitrary distribution, we sample from a very simple uniform distribution that is accurate for the mean anomaly. And then we use relatively straightforward equations and established methods to compute the true anomaly from that. And that's what the code in the next cell after you complete this exercise does for you.
That's right. Thank you, Dmitry. That's where we're trying to head. So I'm going to give you about 5 minutes on this, just because I think it's not going to take you very long, but we'll see how you're doing after 5 minutes. I see about half the room is still concentrating, and maybe half the room is conversing. And so, are you guys ready to move on, or would you like a bit more time? Yes, I see nods for moving on. More, okay, very good. The majority seems to be for moving on. All right, so we are almost able to calculate the completeness function, the probability distribution function. But first, we have to, as Dmitry was saying, we have to compute the true anomaly values. And so we're going to use our previously written code to compute. Okay, so sorry, the point that I wanted to make first was that the Kepler time equation is a transcendental. And so the tricky thing here is that we have to do, you have to invert it numerically. And there are lots of options. There are plenty of options in Python to be able to help out with this, but we're going to use our own implementation here, even though there are other ways that you can do this. And then once we have the true anomaly values, then we can use the code that we previously wrote to compute the corresponding projected separation and delta magnitude. And then we are going to compute the 2D histogram of those values, which involves normalizing and paying attention to our sampling and our bin sizes to make it representative of the true probability density function. And then we will make some fun plots. But first, the true anomaly. All right, so I'm starting by, I ran this cell, and which has this method here to do, to invert the Kepler-Arian transcendental orbits into transcendental time. And then here, note that we're setting the semi-major axis range as well as the eccentricity. And then we are getting, we're computing our observables, the separation and the delta magnitude right here. And then we're going to generate a 2D histogram of the values. And this function gens CPDF, the completeness probability distribution function. If you ever, if you take a peek under the hood there, there's some, that's only the documentation part of it. There's some pretty cool stuff in here about making sure we pay attention to the bin sizes and the normalization so that that's all correct. So on to a plot. It looks kind of like the Bob Brown plot. But what you notice is that it doesn't look exactly like it. And if you look at your neighbors, I suggest everybody to turn and look at their neighbors because it's not going to be exactly like yours. Because here we've only used 10 to the 5 planets. And so your 10 to the 5 planets should be different from your neighbors. If they're not different, then it's weird. Randomized. Okay. And we can look at, let me use this cursor. The delta magnitude that's brightest is right along this edge. And we can certainly see the shape that's taking place here, even if it is a little bit sparse. So we could fill this in by using a ton of examples, but we can also calculate what the bounds are. So let's calculate the bounds. And we can do that by playing the next cell and scrolling back up to the figure. And now we've added the bounds. And note that the theta angle of 90 degrees, that limit is down here along this curve. And then your minimum delta magnitude, i.e. where it's brightest, is down here along the blue curve. And your dimmest delta magnitude is up here at the red curve, and it trails off here into impossibly small delta magnitudes that we could not observe. So to be able to fill in the spaces, we need a lot more planets. And instead of asking your guys' computer or whatever computer Colab is running on in the cloud to calculate those, we have pre-calculated them and offered that data set up for you guys to load. And so that's what we're going to do in the next cell, is we're going to sorry, again, I think I'm getting ahead of myself.
No, you're right. Just
Okay,
fine.
all right. Thank you. All right. It just threw me that there were all these parameters up here at the top, and I was having to reread through this. All right, there we go. So now we've loaded that data set, and it looks a lot more filled in, and it looks a lot more similar to the Bob Brown bird plot. And we're at 10 to the 9 samples, not 10 to the 8. So we filled in all of the space between our minimum and our maximum delta magnitudes. And also we can see that there are no samples outside of our bounding lines. And this plot is called the bird plot because it looks a little bit like there's a wing and a wingtip up here and a tail over here and the head of the bird over this way. Now, the thing is, if we changed our underlying population of planets, like if we changed the range of the habitable zone, or if, say, we did not just Earth exact twins, but we had a distribution of radii for the Earths, and if we had a non-uniform distribution of semi-major axes, we would get a slightly different shape to this plot. But the idea is the same, that we are still that these are our two observables, separation and delta magnitude, and that they do form a joint probability distribution function. And still the highest density of probability is along the bottom line here, where it's brightest, thankfully. And that means that we are now in a position to be able to move on to completeness. Okay, so as Chris pointed out, let me go back to the plot. We can think of our inner working angle and our outer working angle, and that they project onto this plot as limits here, the maximum and the minimum separation that we have access to given our instrument. And then we can also think about our integration time as being a horizontal line. And it may not actually be a line, but for what we're doing right now, we're going to make it a line.
Sorry, Rhonda, that's the next plot. If you can generate the next plot, it has the limits.
Thank you very much, Dmitry. All right, so we can generate that in the next cell. Oh, yeah. And so for this case, we have actually picked some ranges of inner and outer working angle as here we have inner and outer working angle. I'm sorry. This is what we're projecting our inner and outer working angles to be. And then we're plotting it. And let me scroll back down to the plot. And the horizontal line is the delta magnitude that we're integrating to. So if you take everything inside of that box, so you've got 10 to the 8, you've got a probability distribution function in there. And if you integrate inside that box, that should be what your probability of detection is for that size box, i.e. for your inner and outer working angle and for your integration time. So we're going to try it out. And this is your opportunity to write what completeness is, how you are going to sum over that box in the probability distribution function. Now there are some clues here. There's this rectangular bivariate spline. And you may think, what does a rectangular bivariate spline have to do with integration? But if you actually look at the documentation for that function, you'll see that one of the capabilities that it has is integration. And so now I'm going to turn it over to you guys to work, and I'm going to give you 2 minutes for this.
If you're just trying to generate the answer, just instead of calling the local function, call the one from the reference implementation. So just add the preamble, the SSW yield modeling tutorial .calc completeness in the cell that you're on right now.
Hang on, I couldn't quite hear you. It's 10 minutes and I'm hearing a lot of discussion. So I think we have some successful folks out here in the audience who have written a completeness calculation. Congratulate yourselves. Yeah, very good. Pat yourselves on the back for that. Now you can double check it by running the next cell. Because given these parameters that we use as inputs, that should come out to about 0.42. So you can double check yourself there. It's 0.42. Now that's just the completeness for a single star. And you've got to be asking yourself, what about other stars, closer stars, farther stars, brighter stars? So let's take that on in the next section. The first thing that we're going to look at is stellar distance, right? Because that will change our projected inner and outer working angles. So we're going to look at the target star's distance, and we'll look at a range from 1 to 41 parsecs. So
Wait, does everybody know what a parsec is?
Yeah. Dmitry, tell us what a parsec is.
A parsec is a unit of distance. It is defined in terms of parallax, which is the angle of a thing when looked from 2 different directions. 1 parsec produces an angle of parallax of 1 arcsecond with a baseline of 1 astronomical unit, which is really convenient because that's the baseline if you're looking at the same star from the Earth on 180 days apart. So 1 parsec is just a bit over 3 and a bit light years, which means that the closest star to the sun is just a bit over 1 parsec from us.
That's right. That would be true. So 1 AU and the definition of a parsec go hand in hand with each other. And we'll cell, and then we are going to get the bird plot again. And right here we see a squished rectangular box. And as you change the slider, here we go. All right, the distance. So as you get to a farther and farther star, what you can see is that our box is scaling. It's going more towards the right edge of our completeness distribution function. And we're going to keep going. And eventually it just slides off the tip of that completeness function and it goes to 0. So there's a maximum in here. Where is the maximum? It's here at about 6-ish. About 6 parsecs. So those of you for the number with the star catalogs that are of stuff that's closer than 6 parsecs, there's a handful, right? We've got our nearest neighbor, we've got Alpha Cyn and a handful of others. Not a lot. Let me caveat that statement. Let me highlight the note that is here in the text, because there are a lot of assumptions that go into what we just calculated, right? There's the assumption of the underlying planet population, what we think a habitable zone is, the inner and outer working angle of the instruments. And so all of these things are going to impact what you think your completeness is, and even what that completeness as a function of stellar distance is. So let's move forward and look at habitable zones and stellar luminosity. So we're going to change our completeness here for habitable zones. Because as you think about it, so what is the habitable zone? The habitable zone is an idea of like what's the stellar insolation on that planet? How warm is it? Ideally, we think of the habitable zone as where it's warm enough to have water. And so if you have a brighter star, if you have a star brighter than the sun, then you would expect that same radiometric brightness is going to occur further out. And in fact, it goes as a function of the luminosity, the square root of the luminosity. So a sun that is twice, a star that's twice as bright as the sun, as twice as luminous as the sun, would have a square root of 2 further out in astronomical units. Insolation distance, or its habitable zone, would move out by that far, which is what we're expressing in this equation. This first equation, S, the separation, scales as a function of the square root of the luminosity of the star. And we normalize that by the solar luminosity. So we think of the solar luminosity as 1 because we're centric that way. So we can plug that into the delta magnitude equation, and we can see that we can separate out this delta magnitude of the sun, and then we have this 2.5 log 10 of the luminosity right here. So we don't need to actually fully recompute our underlying completeness probability distribution function. We just scale the axes of it. We can scale the delta magnitude axes and have it taken care of. And that brings us then to, okay, and so the way that we're going to do that is that, so now we're going to have, so we have to scale both the X and Y axes. And for the separation, we're going to adjust the separation to be divided by the square root of L. And then the Y axes, we're going to do this delta magnitude offset that we just looked at up here. And that brings us to exercise 5. So you can update your previous completeness calculation function, and now we can add stellar luminosity to it. I bet you guys can do this in 7 minutes. I bet you can do it in 5. Let's take 7. Have at it. Yes, I see a couple of thumbs up. 5, definitely. I think you guys can have this in 5 minutes. I heard a lot of conversations start up about that time. Now there's a little check right down here at the end of this. And so hopefully when you ran your yield code, you got a new updated completeness. It's no longer 0.42. It is now 0.26-ish, just under 0.26. Yes, that went in the downward direction. Because stars that are farther away, we see, we're able to gather in a smaller amount of their completeness curve or distribution function. So it was our chance to add stellar luminosity to this, but we've also been at this for a while. We've been here for an hour and a half. And so this here, I'm voting for a break pretty soon here. But first I'm running here the impact of stellar luminosity. And we have another fantastic slider where we can see as we go to higher luminosity stars. And so we get way out here into some pretty bright E stars. What happens with our box, and then where the ideal match is, the maximum here. Again, those are all the assumptions that we're using. Being able to gather the brightest part of this completeness distribution function. So changing stellar distances is mostly just an impact on the separation, but when they're changing luminosities, that impacts both the delta magnitude as well as the separation. So it's a little bit more complex, and you just want to pay attention to that. And so when we have to say it in a little bit more detail, when we have a lower stellar luminosity, the habitable zone moves inwards, and that they need a tighter inner working angle to be able to access it. I'm inclined to leave it at about that, right? So we had a completeness at around 0.65 solar luminosities, which is like a G star. And as you increase the luminosity, the habitable zone moves out. And so eventually it could exceed your outer working angle. That would be something to pay attention to. But, right, so if we look at our box here and we go super bright, I realized I was reading the index off of the box and not the luminosity. Here we've got like a 18 luminosity star. We're way down, our box is way down here, grabbing just a little bit of the tail. So these are bright Earths, but there's not very many of them in this Monte Carlo cloud. And we come down to something really small, we're only grabbing the tip. And so those are fainter Earths. They're really challenging our inner working angle. One key items to keep on with that. And next up is going to be integration. But I wrote that we take a 10-minute break before starting on integration. Stand up, stretch. I want to say that you guys are doing fabulously. Look, we have computed separation, we've computed delta magnitude, we have computed completeness, right? We've generated the cumulative probability distribution function, which is the joint probability of separation and delta magnitude. And we have adjusted our completeness for stellar distance and for stellar luminosity, and we understand how habitable zone affects it. So we are working our way through a lot of the concepts that you need for yield modeling. You guys are doing a good job. So the thing that we're going to take on next is you may or may not have noted that we've got delta magnitude, and you think that's related to the number of photons that we're getting from the planet, right? But we haven't actually talked about those photons as a function of time and integration time and how we're going to accumulate those photons. So that is what we are covering next. So to be able to do this, we're going to talk about our integration time model, and we're going to talk about signal to noise because we want to do it statistically. Now, different fields may vary on their definition of signal to noise. So from the outset, we're going to be really clear. What we mean by signal, right, is the expected value of photons from our planet. And what we mean by noise is the standard deviation of photons that come from all the other stuff. We'll get to that. Not all of it, but we'll get to a lot of it. So we will think about this in terms of the photon arrival rate. And so for our sources, we're going to call this C subscript P. So that's the C is for the counts, or really we mean the count rate, and P is for the planet. So we're going to have the count rates from the planet multiplied by your integration time is going to give you your total number of counts or your total number of photons. And then we're going to have the counts from the background, which are also multiplied by your total, by your integration time. But that's not statistical yet. So to make it statistical, what we're going to do is we're going to use this definition of SNR here, where the top is the signal. So we've got the counts. You know what? I should be using this other pointer. So that we have the counts from the planet. And what we really mean is like the mean or the average counts from the planet multiplied by the integration time. And then the standard deviation on that is that we're going to take the square root of the sum of the counts that we get from the planet because there's shot noise on those. So really we're saying like what is the standard deviation on the counts from the planet? And then we're also talking about our background sources. We've kind of lumped them all together here under this C sub B. And we can factor out the integration time here. So now that and from up there, so that now that we've got the signal to noise as the counts from the planet times the square root of our integration time divided by the sum of our counts. Let's see. I didn't really explicitly mention this, but our counts from the planet is that we're assuming that there's Poisson noise on that or shot noise. And we're going to assume that that is true for all of our sources. It's going to be true from the counts from the planet, as well as the exozone, as well as the local zone, as well as anything else that would be a noise source. So since the SNR goes as the square root of the integration time, if you want to double the SNR, you have to quadruple how long you integrate for. And it also looks like if you can get to an infinitely high SNR if you integrate for an infinitely long time. There's something in your intuition that says that can't be true. And you would be right. Because usually there is something in your system that will not improve no matter how long you integrate for. And sometimes we call that systematic noise. And for our purposes here, we're just going to call it the noise floor. These are the things that no matter how long you integrate for, you can't average them down because they're systematic. They just accumulate more photons the longer you try and integrate. And so we are going to call that, where is it down here? Okay. And this can get really complicated. So for today, we're just going to call it M. And we're going to add it to the denominator here. And then I have to scroll. Oops. All right, so using these definitions, we can now solve this equation. And which, let me underscore, like I was saying, no matter how long you integrate, this does not get better because these other noise sources here just have T int, but here it's T int squared. Right? That's the way that we're expressing and capturing that no matter how long you integrate on this, it doesn't get better. This noise source doesn't go away. You can't average it out. So we can rearrange this and solve for our integration time. And we get this. And now we've got a minus sign on the denominator, which means that there's a pole in this equation, i.e. there's a point at which it can blow up. There's a point at which it can go to infinity. Because if this term equals that term, then the denominator is 0 and this goes to infinity. So we want to impose a condition because that's not very helpful in our yield code to have that sitting around. So we want to impose this condition that in fact, if these two things equal each other, which is what this equation is here, we're just, that it's unachievable. And we're just going to go ahead and put nans in, not a numbers in for that. And so this brings us then to exercise 6, in which you get to write your own integration time calculation. And then when you're done, you can test it using these provided input values for the count rates from the photons and the background and your noise floor. And we're going to go for an SNR of 5, which is nice and comfortable and easy. And I think you guys could do this in 12 minutes. So let's set the timer for 12 minutes. You want more time? Yeah, okay. See, I thought you guys were going to finish early from the time I gave you. I'm glad to hear that. So let's, how did your integration times come out? How did your check come out down here at the bottom? Did you get the 1400 seconds? All right, very good. All right, I'm seeing thumbs up. I'm seeing double thumbs up with victory. Excellent. I'm glad to hear it. Okay, so now let's talk about modeling the planet count rate as well as the background count rate. And you'll notice here on my browser that I've got a box where I'm supposed to have an F. This is, I hear that this is dependent on browsers. So both Chrome and Firefox don't like to render this. Hopefully your browser, whatever you're using does, but if you don't, this is an F. This is a pretty cursive F in here for flux, because this is the flux of a 0 magnitude star. This is usually actually calibrated with Vega. So, right, okay, so if we're going to actually calculate the counts, we know that we've got the starlight, which is reflected off of the planet. And so we need to know how many photons we're getting from the star. And we can relate that to a 0 magnitude star. That gives us like the number of photons. We want this in flux. We actually want this in photons per second. And then we can multiply then by using the magnitude of the star up here in the exponent, which was a really rambly way of saying that. But okay, so what we're thinking about with the star is our unit of measure here is flux density. And so that is the energy per time per area per wavelength. And so so in order to compute the count rate, we're going to have this flux from the star. And so we'll have a collecting area, A, the collecting area of the aperture. And then we need some wavelength bandpass that we're integrating it over. So that's our delta lambda. And so for chronograph, that might be 20% or 10%, depending on the performance of your chronograph. Because of the inherent chromaticities of it, it's kind of limited to that. This is if you're doing broadband photometric detection. If you're using a star shade, that can be 100%, so you can get a lot of photons all at once. If you're doing spectral characterization, then your delta lambda is going to be, from your spectral resolution, which is lambda over delta lambda, it might be something small. It might be something like 10 nanometers. All right, and then tau here is meant as the throughput of the optics. So you've got the reflectivity of every optical system, every optical surface in your telescope. And whoops, sorry, I clicked the wrong thing and my equation slid off the screen. All right. And then there's a throughput that describes the performance of your chronograph. And this is just meant to describe the core, the throughput of the core of the chronograph. So the losses that you see here are because of the focal plane mask and the Leo mask. We're not talking about the reflectivity of the surfaces of the mirror. And we like to separate them for bookkeeping reasons and because then our chronograph designers can submit just tau core and it can be used in this calculation. And then the quantum efficiency of the detector. So the Q and the taus are, we're really kind of talking about an efficiency here. And so we're going to wrap that up into a single eta further down here at the bottom. Yeah. Down here, eta. That's the end of your 12 minutes. Glad we're ahead of schedule. Okay, so let me also just say something about the effective collecting area. That's easy to calculate when it's a filled aperture circle, but we've seen a lot of different apertures this week that can be used. And so we're going to define this as we're going to take the diameter of the telescope, and then we're going to subtract off whatever that obscuration factor is. So we're looking for that as like a fraction. It's normalized by 1. Or is it 14%? Is it more, etc.? So that'll be specific to the telescope. All right, and we are assuming that every photon that hits produces an electron. So we're not explicitly have so the QE though is really helps keep track of that for us. All right, so now let's talk about our astrophysical backgrounds and the noise that they contribute. All right, so we talked about our signal. Now we're getting signals that we don't want. There's our local SODI, and so we can also so that's the light reflecting off of the dust cloud that is around us in our own solar system. And so it's still going to be collected by the same aperture with the same delta lambda2 and the throughput of the optics. And the throughput here, instead of using the core of the coronagraph, which is kind of trying to express what happens when you have a point source, we have another thing that we call the sky transmission, which is like, what is the transmission through the coronagraph if you have an extended object like the ZODI? And then the other important thing that you need in here is how do you describe the brightness of an extended source? So we usually, we talk about the surface brightness, and here we're calling it Z. And for our local ZODI, we normally use 23 magnitudes per arc second squared as the surface brightness of our local ZODI. And then we have to know like how much of that we're seeing in terms of a solid angle. And that solid angle is defined in terms of our, so we're talking about lambda over D. And then we have to, that's in a single direction. And then we have to square it so that it's solid. It's in all 3 dimensions. The unit of this is a steradian. Right, because the unit of angle in a circle is a radian, and a steradian means now like this 3-dimensional unit, this 3-dimensional angle that we call a solid angle. All right, and then we have stuff that comes from our instrument. In particular, we've got the speckles, the residual speckles, anything that, they not perfectly correct. This is the leaked starlight. It's not perfectly corrected. And so that's going to be the counts from our star. And again, we've got all of our efficiency terms here, and now we're including capital C. So C is what we're using to say what the contrast is. So this is, and expressing the contrast, we're saying like this is the part of the starlight that you don't get rid of. It is like if you're doing 10 to the minus 10, then you have the counts from your star and you multiply it by 10 to the minus 10, and that's the residual that you have in a speckle. And then lastly, we've got the detector, because the detectors have some thermal noise in them. Even when you cool them down, there's little electrons that are just in Brownian motion inside the solid state of the detector. That's happening all the time. So even when you do not have a signal on them, you still have this electron motion inside your detector, and that's called the dark current. And so we have to include what the dark current rate is. So that's also in counts per second. And then usually there's another noise from the detector when you read out the frame. And this usually has to do with digital latches or A to D conversions, or when you're moving charges across capacitive gates. And so it's like click when you move the charge out of the detector. That's what the read noise is trying to represent. And so it's dependent upon the number of pixels. So let me get back over here. So we want to know that, but we don't care about all the pixels on the detector. We only care about the pixels that are where our signal is going to be. So we need to calculate the number of pixels that we have in our photometric aperture. So our photometric aperture is beta beta, and then theta is like the instantaneous field of view of one pixel. So if you were going to take one pixel and project it through your telescope onto the sky, like that's how much angle a single pixel has, and then we have to square it. So it's in 2 dimensions. So the number of pixels that we have in our solid aperture is that solid angle, and then how many instantaneous fields of view of our individual pixels we have in it. You can also call that the detector plate scale or pixel scale. You might know it by that name instead. And so then the number of counts that we get is the number of pixels in our photometric aperture times the dark current rate. So it's fair to note that there's an assumption here that all of these rates are fairly continuous, that the exozodi is giving off a continuous amount of photons, that our planet is giving off a continuous amount of photons, and that the dark current always has this Brownian motion inside of the detector. So these are continuous things that we can just multiply by an integration time. But as I mentioned, the read noise happens just when you read out the frame. And so you kind of need to know how often you're reading out a frame. And so you can set kind of a nominal exposure time for your frame. Now, as we might recall, our integration time is like 1400 seconds. You probably are not going to set a 1400-second integration time on your detector, because if you're in space, you're going to get cosmic rays, and that's going to contaminate your scene, and you're not going to want that. And if you're on the ground, there's just a whole bunch of other things that are going to contaminate an exposure that long, including especially vibration. So you'll wind up setting a shorter exposure time, like 100 seconds or 300 seconds. In space, this is really kind of a rate where you're estimating that we cannot expect to get a cosmic ray in it. So that's really easy for us to toss the frames that have cosmic rays and still have enough good frames. And that is what we're showing. I think that's what we use here, about 100 seconds. So here we set the count rates due to reading the frame is going to be the number of pixels, because that's very important. But that is going to be really our the read noise, and then we're going to divide it by this exposure time. Because I read is really in units of electronics per pixel per readout. And so the per readout is this, the integration time divided by the exposure time. So the last thing that we have to talk about here is the noise floor, and how are we going to handle modeling the noise floor? Now, I've already said that this really represents the thing that cannot be subtracted. It is systematics. It's things that you can't average out. Just integrating longer doesn't help you here. So you're not going to break through this barrier with your current instrument. So we can think about this like based on things that we've heard this week. Maybe one of the easiest handles to give you on this is that we can think about this as being the point spread function and the variation that we have in the point spread function, and specifically the speckles that we have that are residuals that we wish weren't there, but still are in the point spread function. So, and one of the ways that we can get rid of those is through post-processing, right? Possibly with PyClip, possibly with other approaches for RDI or ADI, or using spectral information, but whatever your post-processing is, we're just going to stick in a little factor there that says this is your fraction of how much you're going to improve the counts that you get from whatever your systematic is. And for right here, we're C sub SR means that the count rate from the speckle residual in the PSF is what we're using. And FP is how much your post-processing is going to improve that. So it might be 0.3 saying that my PSF fitting and some traction is going to improve things by a factor of 3. Or you might say, I'm going to improve it by a factor of 10, in which case your FP would be 0.1. And now that you have seen all of the equations, and I hope understand them, it's your turn to get to implement them here in exercise 7. So we have a lot of inputs, and we're going to package those into a few dictionaries. But first, I'm going to define our telescope that we're using. So we're going to use 6 meters. It's very similar to Habitable Worlds Observatory. And we're going to use 500 nanometers and pretend that we're doing photometric detections. And then we're going to calculate what a single lambda over d is for this. And you'll notice that it's pretty small. It's 0.17 arc seconds, right? And that's most of the chronographs can't perform at a single lambda over d. They're likely to be at 3 or more lambda over d. Noting there's just a little thing to say in here about units, because lambda over d is in arc seconds, and some of the things that you're calculating may be in radians, and you may need to translate your units, your quantities here, in which case the AstroPi units will be a friend. So we've got a lot of input parameters. We're going to gather them together in a few dictionaries. Here are the static parameters, things like the telescope diameter and what the obscuration factor is, and the QE, and what F0 is, the zero magnitude flux point of a star. And then we're going to call out how our chronograph performs. And we're using scalar values here, not curves, just a scalar value. And then we're going to talk about our star. So we're going to use a single target. We're going to use a magnitude 5 star. And this is the same Zodi, local Zodi brightness that we talked about. And for the exozodi, we assume that it's a little bit brighter because you're seeing through it, and you're seeing reflected planet light that is coming through it again. And there may also be some forward scattering, so it's a little bit brighter. And now is your turn to implement this function. And it's leading through the steps for A, for eta, for the counts from the planet, and from omega. This is really implementing the equations that we've already gone over. So I think that you can do this in about 5 minutes. Also, we're kind of running short on time for the other exercises, so I'm going to give you 5 minutes. How did you guys do? No, everybody needs longer. So the good news is that you can check your answers in the next cell by your calculation of CP, CB, and M. And that your integration time should be about an hour and a half. All right, looks like you guys are still working, but there's a lot left to cover. So, and I see that we have a slow attrition of people that need to leave at 4:30 and making their way out the door. And so what I'd like to do now is I'd like to cover the rest of what's in the tutorial without taking a break. So we'll cover the next 3 exercises to talk through them. And then with the time that we have it there after that, then you can work through all of the exercises together at once. So the next step that we need to concern ourselves with is how to we invert the integration time. And you have an important decision as the designer of your mission at this point to make. And that is, how much time do you want to spend observing your target stars? So this is really a question of how are you going to allocate your resources? Because mission planning and survey design is really all about resource allocation. So you can take approach number one, which is you're going to integrate to the same delta magnitude on every star. And that means, like, if we go back to the bird plot, everybody's going to get the same delta magnitude, right? Because we think of an Earth twin at quadrature being a delta magnitude of 25. So we're going to integrate everybody to that, and then we'll be able to say, did we find an Earth or not? And there are pros and cons on each of these, right? And kind of the pro on this one is that you can really say something about, the planet population in that survey. You're like, well, we looked at every star to that level and we didn't find any planets, so it's probably not there. Now, the other approach that you can do, though, is you can say, hey, I've seen how that box moves around with luminosity and with distance to the star relative to our bird plot. And, if we've got a really bright star, then we're going to have to integrate for a long time. If we have a really dim star, and the working angle is going to be a problem. So why wouldn't we tailor how long we're going to integrate to every single star? So you can do that, and you can find the optimal point for that particular star. And then, so you might be able to actually visit more stars that way. And then you're not blowing integration time integrating to delta magnitude on a 25 on a star that's really hard to get to a delta magnitude of 25 on. That's true, but what we're talking about here is statistical because we're running the simulation. It's statistical in nature, and so you'll come up with, okay, so I'm going to see 0.3 of a planet around this star, and when we make these observations in reality, we don't see fractions of planets; we see whole planets. So there are pros and cons to each of these approaches. There are more delineated here in the text, and you can implement them in different ways. So if we're taking approach one, we can just select our target delta magnitude for the survey and directly compute the completeness value and the integration time associated with that. But if we take approach number two, then to compute the achieved completeness as a function of integration time. And so we also have to be able to compute the maximum achievable delta magnitude for a given integration time. And we do that by inverting our integration time calculation. And the current model that we're using is simple enough that we can do an analytical inversion of that, go us. And then we can implement that and solve for the counts from the planet relating it to delta magnitude. And that is what exercise 8 is about, which is implementing a method to compute the largest achievable delta magnitude for a given integration time. And we keep pretty much the same inputs. And we call CD and M, and right. So we're going to take the time to do that now. You can double check yourself and see that your delta magnitude should be about 26. Because I want to make sure that we have time to talk about the target list. For our purposes of the tutorial here, we're going to use a target list that was put together by the Exoplanet Program Office, project scientist and deputy project scientist for Habitable Worlds Observatory. And their purpose in this list was not to use it as input for yield calculations. I want to say that first off. It was to say they thought these are the most likely stars that HWO is going to look at. So people that are interested in characterizing stars should go characterizing these stars now. It's 164 planets long, and for our purposes here, we're actually pretty happy to have a short target list. So we're going to go ahead and use it as an input for yield modeling right now. You run this first cell to load it, and you can see that it's got information on the different properties of the stars. And then we can compute the completeness for each of those stars. And yes, so we're getting the minimum and the maximum and the mean. And we see the minimum is pretty small, and we see that the mean is only 0.2. And it would be nice if that mean were higher. Um, so let's visualize it. And so we can look at it on the sky like this, colored by the completeness. So we see that we have a handful of these, only a few of these yellow high completeness stars, and then we've got a bunch of these mid-range completeness stars, and then a bunch of low completeness stars. Okay, so how long would it take to actually integrate on all of these? Because now we know how to calculate integration times. So we're going to, instead of calculating integration time for a single star, we can calculate it for every single one of these stars and plot it. And if we visited each of these stars once, it would take 6.5 years or 6.25 years. So for a 5-year mission, that blows the mission. And we've only looked at each one of these once, and we've only done photometric detection. We haven't even taken any spectra of any of these. So again, this underscores the importance of survey design and mission design is making decisions about how you allocate resources across your target list. And then there are other things that you can do, which is to go back to your drawing board about how you design your coronagraph. Maybe you want more throughput. Maybe you want a bigger photon bucket. Maybe you want a higher QE detector. Maybe you want a longer mission. So let's talk about mission constraints. Because one of the things that we want to calculate is it feasible to make this observation? Because some of these stars are going to be more feasible than others based on where they are in the ecliptic. And so for an observatory, which is in a halo orbit at around Earth-Sun Lagrangian point 2, which is where JWST is, we have this diagram. And the important thing to know here is that the telescope can't look into the sun because it's going to fry itself, and you never want to do that. So every telescope in space has a solar avoidance angle, and like 40 degrees is a pretty typical value. It might be 45 degrees. So you have to stay out of, so that's this yellow cone that points to the left side of the screen. You have to avoid the sun this direction. And then you might have an anti-sun angle for several different reasons. One, your starlight suppression system might be a star shade. And if that's the case, you don't want to put the star shade opposite from the sun, because then it becomes a mirror and you're reflecting sunlight into your telescope. And that doesn't give you high contrast imaging. And it could burn your detector. Or you can have solar panels that absolutely need to continue facing the sun, and you can't point them all the way away from the sun. Or you can have a solar radiator that needs to not point to the sun, and it has to always point against the sun. So we can just toss all of these together in what we call the anti-sun angle. And this example here is for star shade, and so this white area is your field of regard. And also, as time propagates, this whole reference frame we're just imagining is rotating around the sun. So we've got the sun to L2 point, and this whole reference frame is just going to propagate through time. Wow, there's a bad lag on this. All right, well, so it's going to rotate that way. And you guys get to figure out how to calculate what those keep outs are. And we call it a keep out map. So we've got one that you can load up, because the fun thing is to interface with it. And so this is the one that we've provided that you can look at. And the important thing to know is I think that green is when they're available. Let me double check. Yes, green is when they're available, and black is when they are not available. And I think that this might be the keep out map for the Roman Space Telescope. So stars are unavailable for a lot of the time, and there's some structure to this. And in fact, we can sort that by ecliptic latitude to see what the structure is. We're going to do that, and we reveal this very pretty structure. And then we're going to make a plot over a whole year. So now ecliptic latitude is on the x-axis, and the target availability in days is along the y-axis. So we have targets that are available for like a minimum of 100 days. And really, that's like if it's on the ecliptic latitude, if you've got like from 45 degrees away from the sun to maybe 90 degrees anti-sun, that's 45 degrees. And then on the other side of the sun, you've got those same 45 degrees and you total those and that's 90 days. So that's in essence the regime that we're talking about here. Or if you have stars that are up at the pole, they're really not badly impacted by the anti-sun angle and you can see them anytime. I'm rounding here in my statements. All right, so exercise number 9 is how to be able to interact with the keep out map. And you can, this is an exercise to check the indices of when your potential observing windows begin and end. And they're cyclical with 1 year. And then there's an opportunity to check that. And then, so when I finish here, you'll have more time to be able to work on these while we are all here together. But let me wrap up the concluding remarks on this, which is that we have built a lot of bricks that are how you do yield modeling right here. And what we're really after here at the end is the sum of the completeness over your ensemble of stars. However you've allocated your integration time, you get a completeness for every star, you sum it, and then you multiply that by eta sub Earth. And that gives you a yield or an expected number of exoplanets to be seen with what you've designed for your mission and your resource allocation policies and decisions and your instrument and your coronagraph. And that is how we get to a yield. Now, of course, we can make it more complicated. But we want to give you an opportunity so that hands-on, I want to give you a little preview of the group projects tomorrow is that you'll have 2 choices if you want to work on yield modeling. One of them is that you can work on how to optimize allocating your integration time for yield. And the other one is that you can focus on how to schedule your mission. And so how to allocate your observing time on a per star basis. And then so what we've covered here are all the building blocks for yield code, but we haven't actually covered how to do exosims. If you are interested in actually exercising exosims as a yield code, it's open source, it's on GitHub. We would love to welcome you as a developer contributor to it. And if you don't know how to get started on it, there is some nice documentation for for a quick start guide, as well as the more thorough documentation for exosims. And I'm also happy to help introduce, do a more thorough helping of anybody that wants to get started on exosims. So let me end here and free the time up to you guys to continue working on any of these exercises. And our helpers and I will continue to be here to help you work through the exercises. Thank you. I should ask Dmitry if he has any concluding remarks that he also wants to fill in. If he's still with us.
I am, but my house lost power a little while ago, so I'm speaking to you on battery power. I'm actually shocked that I still have internet. But anyway, thank you all for participating in the tutorial. Hopefully you got something out of it, and hopefully some of you will want to work on the group projects. In addition to this, we actually have another one of these tutorials for exosim specifically that Rhonda can point you at. Yeah, the real focus here is just on these building blocks. And if any of you want to get in touch with any of us after the session with any questions, please feel free. Our emails are kind of everywhere online. That's it. I think my computer is about to die. So thanks, everyone.
Yeah, thanks, Dmitry. You reminded me that I should introduce you guys to this resource also, which is the yield modeling tool workshop that we held at the AAS in the winter. And we also had one in June earlier that year. And there are some fundamental concept videos here that's like a 10-minute talk on each of the fundamental concepts by the experts. Except that the talk about integration time models is 45 minutes long. We broke it into 3 sessions. That's just how complicated integration time models can get. And then there's also a different, there's a tutorial here on exosomes and how to get started on exosomes. And if you want an overview of what exosomes is like, then there are also recorded talks down here. Dmitry gave a half-hour deep dive on exosomes, and then Chris Stark gave a 20-minute deep dive on AYO. And then there's also a tutorial on ExoVista, the image simulator. So these are also resources for you. Thank you. And you guys did great, and you should give yourselves a round of applause for doing that coding and working through the hands-on tutorial this afternoon. Good job.